So in this short video, I will show you the relation between the Fourier series, the Fourier coefficients, Parseval's identity from one side, and linear algebra from the other side. If you remember, I asked you many times in class how many of you have attended the linear algebra course, and many of you have done so. So I think it's very convenient to show you the relation, how we think like the whole picture, the big picture about the Fourier series. So my little title will be linear algebra and Fourier series. What was linear algebra about? It was about matrices, then vector spaces, and orthogonality. So let me remind you, what do we mean by orthogonal functions? When we talk about orthogonal functions, the term orthogonal is usually referred to vectors. So for example, if you have a vector, another vector, if you have a 90 degrees angle, then we say the two vectors are orthogonal. Now, the extension of this concept to functions or to other objects is done using what's called inner product spaces, a topic that you did in linear algebra. So when we deal with functions, remember there is the inner product. So if C negative pi is the space of continuous functions on negative pi, we define the inner product of G as the integral from negative pi to pi f of x g of x dx. Now, why did we choose the interval negative pi? Because this is our reference interval in Fourier series. Of course, you can select any other interval. You can say, let's see, AB, so you can select any interval AB, and you do the same computations that I'm going to do in this presentation. So let's take this inner product. I'm sure most of you saw this inner product in linear algebra. You tested this as being an inner product, so it satisfies all the axioms of the inner product. So I'm not going there. I'm not going to show you that this is an inner product. Let's remember some notations and terminologies related to this inner product. What do we mean by orthogonal functions? So if you have two functions, f and g, they are called, so two functions f and g are said to be orthogonal if f inner g is equal to 0. Remember, this is like the natural extension of the well-known criteria for orthogonal vectors. So if you have two vectors that are orthogonal, let's say u and v, how do you tell that the two vectors are orthogonal? You compute the inner product, right? The dot product is 0, then the two vectors are orthogonal. Now, the extension of this to functions is that you compute the inner product. If the inner product, which is defined in this example by the integral, if it's 0, then we say the two functions are orthogonal. Now, the nice thing is that if, let's say, f1, f2, f3, up to fn are orthogonal, then they are linearly independent. Of course, none of the fi is 0. We shouldn't have any 0 function with them. So again, this is one of the basic results in inner product spaces. The way you can look at this, just look at the I, J in R2. So if you look at the unit vector in the direction of the x-axis, the unit vector in the direction of the y-axis, these two vectors are orthogonal and they are independent. Of course, the other direction is not true. So if you have linearly independent vectors, they're not necessarily orthogonal, but we can make them orthogonal by applying the Gram-Schmidt process. So we obtain new vectors that span the same space as the original vectors, but the new vectors are orthogonal. If you look at ijk, so this is ijk in R3, again, these are orthogonal vectors and they are independent. Now, in general, in any inner product space, if you have orthogonal vectors, those vectors are independent necessarily. Now, if they are independent, that means that these functions form a basis for a certain subspace. What do we mean by a basis and a subspace? Of course, this is a big topic in linear algebra, and again, I'm assuming you are familiar with these terminologies. But simply, this space or subspace, it is the set of all linear combinations of the fi's. So that means you take all possible numbers multiplied with the first function, all possible numbers multiplied with the second function up to the last function. Now, what are the alpha i's? If you are dealing with a real inner product space, they are real numbers. If you're dealing with a complex inner product space, these are complex numbers. So let's say we're dealing with real numbers. So now the idea, if fi and the I is from 1 to n, so if you have n functions that are, so if this is an orthogonal set means every pair of functions from this set is orthogonal, so the two functions are orthogonal to each other. So if this is an orthogonal set, and if you have a function different from those functions, or maybe one of them, but usually it's different, is equal to a linear combination of these functions, then there is a formula for this alpha I. If you remember, the alpha I was f composed with inner product fi over fi square, if you remember. So let me show you at least how we obtained this formula in linear algebra. So please, just to show you how this formula works, let's look at R3, for example. Okay, let's look at R3. In R3, any vector v, for example, v is 3i plus 4j, for example, minus 5k. Let's say we have this vector. Now the I, j, and k, these are orthogonal. So I'm saying the I, j, k, like they play the role of the f in this statement. So I'm now talking about f1, f2, f3. I'm trying to generalize the concept of orthogonal vectors to orthogonal functions. So now the I, j, k are orthogonal, fine. Now what happens if you make the inner product between v and I? What do you get? You get 3i plus 4j minus 5k inner product with I, right? But this is equal to 3i with I plus 4j with I minus 5k with I. But the inner product of I and j is 0, and this is 0. So basically what's left is 3 times the inner product of I with itself. Now, what is the inner product of I with itself, or the dot product? It's the magnitude of I squared, but the magnitude of I is 1, so this is basically 3. So what is this? So what is the 3? The 3 is v, the vector, with I over the magnitude of I squared, but in this example, because the magnitude of I is 1, it is 1, so we don't write it if you don't like to write it. So if you look at this formula and you compare it with this formula, we are talking about the same thing. So this is like the new concept with orthogonal functions. It's not a new concept. It is a generalization of the well-known and familiar concept in vectors. So now, let me show you again with functions what happens when f is equal to this. So it's a linear combination of certain functions, certain orthogonal functions, and I want to show you how to obtain the alpha I. The idea, so this is just a little proof. If you perform the inner product between f and fi, what do you get? So f is alpha f1 plus, at a certain point you will meet alpha I fi, you will continue to alpha n fn. If you make the inner product with fi, what is this? This is alpha 1 f1 fi. You will meet at a certain stage alpha I fi up to alpha n fn fi. But because those vectors are orthogonal, so the f1 with fi is 0, the fn with fi is 0, so the only non-zero term is when you have I with I. So this is alpha I, fi, because the vector is not orthogonal to itself. But what is this? This is exactly alpha I times the norm of fi squared. So from this, what is the alpha I? If you divide, it is fi over the norm fi squared. So this is exactly what we have in this formula. Okay, so this is the little proof of this formula, and again, this is just the extension of the well-known result for vectors. Let's delete this. Okay. Now the big result that's beyond the level of this course, so it needs a lot of analysis to prove, but let me state it here. So this is a big theorem in real analysis, is that if you look at the functions 1, cosine x, cosine 2x, and so on, cosine 3x, 4x, and so on, and sine x, sine 2x, and so on, the theorem says is that this is a basis for the space of continuous functions of negative over negative pi. So if you take all continuous functions, what do we mean by a basis? That means you can write it as somehow a linear combination of these functions. Now what's more important rather than being a basis is that in fact, if you take this set, this set is not only an independent set, but it is an orthogonal set. So to prove that this is an orthogonal set, what we do is, for orthogonal set, we mean every two different functions are orthogonal to each other. So what we need to do is, you take one, the function 1, this is the function 1, you take it, you compute its inner product with all other functions. So you take this one, you perform the inner product with the infinitely many functions, then you take the cosine with all other functions, the sines with all other functions, and so on. So this is what I'm going to do quickly in here. So if you take the function 1 and you compute its inner product with cosine and x, so n could be 1, could be 2, could be anything. Now what is our definition for the inner product? Our definition is the integral from negative pi to pi, f of x, the first function is 1, the second function is cosine and x dx. But if you compute this integral, right away it is 0. So what this statement says is that, so what this means is that the function 1 is orthogonal to all the cosines, okay? Then, we need to check 1 with the sines. But again, if you compute this integral, 1 times the sine, you will get 0, and what this says is that the function 1 is orthogonal to all the signs. Then, so we finished the one. So the one is orthogonal to every other function in this set. Now what we need to do is to take, for example, cosine x and to say it is orthogonal with all other cosines and sines. So I need to take cosine 1x with all other cosines and sines, cosine 2x with all other sines and cosines, and so on. So what I'm going to do is, if we take not cosine 1x and then cosine 2x, so in general, if you take cosine nx and you want to test it with cosine mx, of course, with n is not equal to m, because when n is equal to m, they're not orthogonal. Orthogonality means two different objects are orthogonal to each other, not the same object with itself. So if you take two different indices, n and m, and you compute the inner product, so this is minus pi to pi, cosine nx, cosine mx, dx, and again, n is not equal to m. I'm not going to write it again. So how do you compute this integral? This is just a standard integral. It is 0, we know it. But how do we compute it? It's half the integral minus pi to pi. We use these identities. It's n plus m x plus cosine n minus mx. And now if you compute this integral, it's half. What's the integral of cosine? It is sine n plus m over n plus m plus the other sine from negative pi to pi, and nicely this is of course this is equal to 0. So what we've shown here is that cosine mx is orthogonal to cosine nx, of course, when n is not equal to m. So again, remember, I'm trying to show orthogonality of this infinite set. So what we've done so far, we started with the 1. We proved that the 1 is orthogonal to all other functions. Then we started with the cosines. So we proved in this number 3, in bullet number 3, we proved that the cosines are orthogonal to each other. Then I want to show that the cosines, so those cosines, are orthogonal to those sines. So in my next computations, I want to look at the cosines. So if you take any cosine and you compute its inner product with any sine. And again, so the first one is n, the second one is m. But the n and m here can be the same, because if n and m are the same, the two functions are not the same. We're talking about cosine and sine. So we're talking about cosine x and sine x, cosine 2x and sine 2x possibly. So again, how do you compute this inner product? It is the integral. And we know that the cosine is even, the sine is odd, the product is odd, and the integral is 0. So we've shown that the cosines are orthogonal to the sines. Now what's left is to test the sines together. So I'm taking sine with all other sines, but here I need to require that n is different from m. So this is the integral from minus pi to pi, the sine times the sine. And if you compute this like the computations we did in number 3, you will get 0. So we're talking about sine nx is orthogonal to cosine mx when n is not equal to m. So these 5 steps show us that this set here is an orthogonal set. Okay, so this is an orthogonal set. Now remember again, in this theorem says that this set is not orthogonal. The theorem says, okay, we know that it's orthogonal. It is a basis for the space of continuous functions of negative pi pi. So that means somehow, so my conclusion is, so 1 cosine x, cosine 2x, and so on, sine x, sine 2x. So this is an orthogonal set not only is an orthogonal set, and any function f that's continuous on minus pi pi can be written as a linear combination of this orthogonal set, right? This is what a basis means. This is the meaning of this theorem here, that these functions they make a basis for the space of continuous functions. So basically that means if you take any functions continuous on native pi pi, you can write it as a linear combination. So what's a linear combination of these infinitely many functions? You take a number, you multiply it with 1. So for example, you take alpha, multiply it with 1. Then you take another number, call it beta, you multiply it with cosine x, and then gamma with cosine 2x, and so on. But because we have infinitely many functions, I will not have infinitely many letters. So I need to change my notation and maybe say, okay, take the 1, multiply it with a number, call this number a node. Then take the cosine, multiply it with a1. Take cosine 2x and multiply it with a number called cosine 2, and so on. Then go to the sines and multiply them with b's. So b1 sine x, b2 sine 2x, and so on. So if you look at this, what is this? This is exactly a node plus the sum from 1 to infinity for an cosine nx plus bn sine nx. And this is exactly the Fourier series. So the idea of Fourier series, in the back end of the Fourier series, we have some notations of linear algebra and orthogonal vectors. Fine? Okay. Now what about these constants? So now I want to find a node, an, and bn. How do we find this? We go back to this remark here. So remember we said that if you have a function written in terms of orthogonal functions, so I'm looking at this line now. So if you have a function written in terms of orthogonal functions, then this is the formula for the alpha i's. So the coefficient of f1 is found by this formula. You just replace I by 1, okay? The formula for alpha 2 is found using the same formula, but I is 2, and so on. So now if you want to compute, for example, a node, what is a node? You just apply that formula, okay? You just apply this formula. So if you like, I can write it here just for reference. So this is the alpha I formula. So what is the a node? The a node is the function with fi. Now what do we mean by fi? Fi is the function that we take from the orthogonal set and we multiply with alpha I. So alpha 1 is multiplied with f1, alpha 2 with f2, and so on. So in my case, in the Fourier series case, the a node, what is the function that we multiplied the a node with? The function was 1, right? So now we take f and we make the inner product with 1 over the magnitude of 1 square. So what is this? This is 1 over the magnitude of 1 square times the integral minus pi to pi f of x dx. And now the question is, what is the magnitude of 1 square, right? So now what is the magnitude of 1 square? The magnitude is 1 with 1 inner product, which is the integral from minus pi to pi 1 times 1, which is 1, and this is exactly 2 pi. So basically what is this? So 1 over magnitude 1 square is 1 over 2 pi, and then integral minus pi to pi f of x dx. What is this? This is a node. This is exactly what we have in our formulas in Fourier series, right? So this is how we computed the 1 square. Okay, let's move to the an. So what is an? An, again, I'm going to apply this formula. So the alpha I, this was my formula, f with fi over magnitude fi square. What is alpha I? Alpha I is the coefficient of fi. Now, if you want to find an, what is it? An is the coefficient of cosine and x, right? So now the fi is not fi, it's cosine and x now. So basically I take the inner product of f with cosine and x, and then we divide by cosine and x squared, the magnitude square, which is 1 over the magnitude square times the integral negative pi to pi f of x cosine nx dx. But again, you need to compute the magnitude of cosine square. How do you compute it? You say, okay, the magnitude of cosine nx square is the integral minus pi to pi, the function times itself. So it's cosine square nx dx, which is half integral 1 plus cosine 2nx dx. This term gives 0, and this integral is 2 pi over 2, that's pi. So that's why we have here 1 over pi integral minus pi to pi f of x cosine nx dx. So again, this is a node, and this is exactly what we have in our Fourier series formulas. Now, using the same logic, so similarly, if you compute the Bn, it will be 1 over pi minus pi to pi f of x sine nx dx. So this is how we look at the Fourier series as a special case of the more general concept of orthogonality. Fine? Okay. Then let's look at Parseval's identity. Again, from linear algebra, if you have an orthogonal set, so f1, f2, up to fn, if this set is orthogonal, and if you take a function that is a sum, a linear combination of these functions, so alpha 1 f1, alpha 2 f2, up to alpha n fn, then if you compute the magnitude of f square, it will be the sum, let me write it this way, it will be the sum of the alpha I square and the magnitude of f square, the magnitude of fi square. What is this exactly? So let's see a little proof so you understand how we obtain this formula. So what is the magnitude of f squared? It is the inner product of f with itself. So basically it is alpha 1 f1 plus up to alpha n fn, then the same thing. But if you distribute, because then this means that alpha 1 f1 inner product alpha 1 f1 plus alpha 1 f1 inner alpha 2 f2 up to let me delete this just to save space, so all the way up to alpha 1 f1 alpha n fn. You do this thing for all the functions, so it's like you are distributing parentheses. So the next one, for example, will be alpha 2 f2 multiplied with all other functions, alpha 1 f1 and so on, up to alpha n fn, alpha 1 f1, all the way up to alpha n fn, alpha n fn. But because the functions are orthogonal, so that means if you look at f1 inner fn, it will be 0. f2 inner f1, it will be 0. But in the first line here, alpha 1 f1 with alpha 1 f1, this is not 0, right? And please, I'm dealing with real numbers, so the alphas, everything is real, just to simplify the case. The complex case is the same thing. You just insert the conjugate to the inner product. So basically, the first term, this term, gives me alpha 1 square and then f1 inner f1, which is f1 square. Then a plus. In the second line here, I have alpha 2 f2 with alpha 2 f2, and that is alpha 2 square magnitude f2 square, and all the way up to the last term, which is alpha n square fn square. This is exactly this. Okay, this is exactly this. So this is reminding you. This is just a reminder of this basic identity of orthogonality. Okay, so now if you take a function and you look at its Fourier series, so this is a node again, plus the sum from 1 to infinity, an cosine nx plus bn sine nx. And let's compute the magnitude of f squared. What is the magnitude of f squared? The magnitude of f squared, according to this, because now my functions here, remember the a node is multiplied with 1, and then you have the cosines and the sines. These functions are orthogonal. So according to this page, if you write f as a linear combination of certain orthogonal functions, then you can compute the magnitude square, which will be the summation so it will be a node square, then times the magnitude of 1 square plus the sum an square magnitude of cosine and x square. Let me write it in a new line. So plus the sum from 1 to infinity an square cosine nx magnitude square plus bn square sine nx magnitude square. Okay, but this is equal to n square. What is the magnitude of 1 square? We computed it here. So the magnitude of 1 here in the last line was 2 pi. So this is times 2 pi plus the sum from 1 to infinity. Now what is the magnitude of cosine square? We computed it here. The magnitude of cosine square is pi, and the same for sine square. So this will be pi an square plus pi bn square. If you factor the pi, you will get pi times 2a node square plus the sum from 1 to infinity an square plus bn square. And if you rewrite this, this is 1 over pi, so I divided by pi, 1 over pi. Now the left side is the magnitude of f square, which is the integral from negative pi to pi, the function square dx. That's equal, after dividing by pi, that's equal to 2a node square plus the sum. And this is, if you look at this identity, this is exactly Parseval's identity. Of course, in the real case, what do you mean by in the real case? If my function is real, if all my constants are real. What is the difference if we're dealing with C? If you're dealing with C, just a remark, if you're dealing with C, then the inner product becomes the integral from negative pi to pi f of x times the conjugate of g. This is the only difference. In that case, when you multiply things together, instead of multiplying, for example, a node with a node, you will end up having a node with a node conjugate, and that will give you the absolute value or the magnitude of a node square. You can do these computations by yourself. So again, the purpose of this presentation is to show you some relations between linear algebra, for those of you who studied linear algebra, or maybe who are studying now linear algebra, and the Fourier series. So this is Parseval's identity, and this is the Fourier series itself. That's it.